Good afternoon, everybody. So thank you very much for introduction. So I am going really to speak about our attempts and our efforts to work in the partnership with Transvalor. And I would say that thanks to Transvalor in collaboration with CMF also, because actually it was Transvalor who introduced us to CMF, and we actually getting a lot of support and a lot of exchange of experience with CMF too. And this is we, as I was telling yesterday at the pitch, and we are sitting in between industry and university. So this partnership is exactly what we have to do. We have to make the full adaptation of the things which are developed in the institutes for the needs of the industry, such that it will be really possible to do in the real industrial processes. So in our center, we have very many things at a time. We have all kind of industrial trials. At the same time, we have microstructural characterization. We have mechanical tests. We have all kind of design issues. And actually, modeling plays a very, very big role, because this is the language in which all these parts are actually talking to each other. And we are very lucky. We have almost all possible software which can calculate something, and proud to have NXT Forge and DGMU with us. But here is a little problem, that you can be very rich, you can have very, very fancy and very powerful car, but if you are getting into the traffic jam, it is hardly the question of the capacity of your car if everybody are standing. And this is the question which was raised few times in yesterday and today discussion. It is the question of the main bottleneck of all simulations. It is the question of calibration of the models. It is the question of calibrations of phenomenological models. It is the question of finding material curves for finite element modeling. It is the question of finding parameters for fracture mechanics. So problem again and again remains the same. And because of this, we feel that this is the very important field where we need to do the efforts. And at the same time, we understand that it is the battle which is a bit too big for one particular organization. And here we think that the efforts of different companies, different institutions who are dealing with this have to be combined. So what is the result of poor calibration of the models? If you will pay attention at this, you have the left and the right. This is forging of the disks, standard hot forging. Very well-known processes, very well-known models, and again, we want to get the prediction of the defects, which are some localization, shear bands, underfilling, and again, we are getting something like the picture at the left, where we have everything nice and smooth until we do the first forging. Similar situation happens with microstructural modeling. This is the benchmarking which was recently done in Advanced Forming Research Center. So we have asked many different companies and many different software providers to make the prediction of the microstructure using those models which they have with the parameters. We have chosen the very standard material in Canal 718, which is well known, almost everybody have, and you can see in the most left column it is strange. It's reacts on the no. So in the most left column you can see the experimental data, And so it is two different kind of equipments, hydraulic press and screw press, so it is already industrial equipment. And you can see the real zones of recrystallization in the experiment, and you can see the prediction. I don't write here which column belongs to whom, but actually, as you can see, it does not matter. There is no champion in this competition. So all predictions are bad in this or that sense, and it means that if we want to use our modeling as the predictive one, we definitely need to do something about this. And all the reasons, all the main background of these problems is almost all what we have now in terms of the curves, almost everything what we have now in terms of microstructural data, actually is originated from the laboratory uniaxial tests. The idea of this test is, of course, absolutely clear. We want to have pure form of deformation, we have pure phenomenon, but if you will see at this disk in this picture and the points 1, 2, 3, and 4, you can see that if we will plot their trajectories in terms strain rate, temperature, and strain in this graph, we will have quite complicated curves. At the same time, if we will take our tensile tests, what we will have? We will have these small, short, red lines. And these short red lines can be mainly at quite low strain rates. If we will go above strain rate of 1, it is very tricky to get even this short line. So our chances to predict everything, all this complicated, on the basis of these small pieces of information, from my point of view, are quite low. And it means that whether we like it or not, we again and again dealing with the same what was discussed today in the first lecture of Professor Tekaya, that we have to extrapolate data, and this is always very risky because we don't know what is happening there. But if in the cold forming we have some tricks that we have make, as it was told today, for example, extrusion, and then from extruded part we are getting the specimen and make further deformation. When we are coming to the high temperature deformation, it is very difficult. I can stop the experiment, but when I will be cooling it, cutting the specimen and then heating it again, very big part of the microstructural changes which are there and which define its behavior actually will be vanishing. And so I am again not getting proper information. So because of this, may we like it or not, we are again and again coming to the question that we need something more than simple calibration on the basis of lab test. Of course, in this case, it would be nice to have coupled equations such that we put some parameter which deals with the microstructure into this equation. So our microstructure transform, and correspondingly, our stresses are also changing. So this brings us to the need to look at the microstructure very, very careful. And we have the choice either to go to classical phenomenological models. GMAC is one of them, there are a variety of them. Or we have to go to something more scientific, more complicated, like multi-scale modeling. For example, full field model, which is there. Of course, being close to the industry, we would always prefer to stay in the first with the phenomenological equations. It is easier, it is simpler, it is more clear. But as you will see now, it is not always possible because actually here are all the time the same problems. We have a lot of constants here and there. Then the second thing, when we need to find these constants, very often the experiments which are prescribed for us are very tricky. It was told, Pascal have mentioned, that one of the services which we do for our customers is defining the material characterization, defining the parameters of the models. So it is very costly for the customer in any case and very difficult for us to do because these experiments are very, very, very tricky to do. It means cost, then they are not very robust, repeatability can be low. So it makes us to think whether we can have anything alternative. For example, here is tensile test. I want to find the yield stress or, for example, peak stress. You can see tensile test at the top and compressive test at the bottom. We have different shape of the curves. It can be no pronounced peak in the curve. So it can be many, many different problems which, if anybody is interested, we can discuss at our stand. And I'm going further, and this is the question: can we suggest something new, something different, something completely different from lab test? And here the idea which we have is to try to get some information directly from the forging test. So you can see here in the videos, it is our forging in the hydraulic and the screw press. So it is almost all the conditions which you have in the industrial one: 500-ton hydraulic press, 2,100 is screw press. The only difference here, you can see that there are thermocouples. So we are doing industrial test, but add to it more metrology, such that we more accurate know all the conditions which are there. So, and we are getting all the details and all the information. From one hand, of course, we have one big drawback, because it is not any more homogeneous deformation. So it means that we cannot say that it is constant strain rate, constant temperature. We have complicated history. We cannot say that it is only dynamic recrystallization or it is only recovery. So we have the mixture of everything, but we have some benefits from it, because at the same time we can see different states of the material deformation and different states of microstructural transformations. So we can see some boundary between, for example, not recrystallized, recrystallized, and we can see the kinetics how this recrystallization develops. So it is cheaper, definitely, because if suppose in one day I can do 2 high temperature lab tests, these forging parts I can make 20 or 50 per day. The second thing is that, of course, it is much more repeatable. Again, the benefit that, for example, if you will see the GMAC model, theoretically I can do calibration from a single test which is there. Here, again, I will go very brief because I don't have much time. This is our way how to take into account everything and to make our finite element simulation as close to the reality as it is possible. So this is the way how we are developing the digital twin. And on the basis of this digital twin, we are plotting these zones where we have, so we have ABSD from one hand, digital twin from another. On the basis of 2 of them, we can make these pictures. So we have the big set of experiments. And finally, for each point where suppose recrystallization started, or for any point, we are getting the trajectories. So we have that history of the strain rate and temperature, which to be put into, can be put to the DGMU as, for example, Pascal was telling. But of course, as you can see, that this complexity of the process makes us very far from the chance to improve GMAC model. We can improve it, but this is the limit of this improvement. And it is pretty clear that it is needed something more, something different to be able to go further with this. And so, something more, something different, it means that our recrystallization, it is not simply some accumulated plastic strain. You can see that if you will see these different points, in these different points, you will see different deformation of the microstructure. So it is exactly what DigiMu is trying to take into account. So because of this, our logical decision was to go to DigiMu. And here again, I should just acknowledge the respect to Transvalor company, because everybody needs to understand that till today's day, multi-scale modeling was mainly the point of research. It is mainly research institutes. It is mainly a research where we were simulating. It is maybe for the first time, it is attempt to make these research value things to be brought to the engineering level, to the level of the industry. And of course, it is a very long and very complicated journey, but I would say that on our attempts make at least me optimistic that I think that it is doable, that one day we will be able to describe a real industrial process. So, what we are doing here and what are our efforts to do in collaboration with Transvalor and CMF to do. So first of all, we are doing these things such that, again, to be oriented to our customers. Because, for example, the first thing that EBSD is now less exotic than it was 5 years ago, but still it is the question of the processing of EBSD images. So first of all, we are making the sort of the small pieces of the automatic processing of the standard EBSD image. For example, this is the some GUI which is prepared for you to get the crystal suitable for DigiMu from the standard EBSD image. So it will be cleaned, all small grains will be removed, and you will have something which you can use directly. Then the second thing, it is recommendations. For example, everybody knows what is average grain size, but then the question is how do we calculate it? By area or by frequency? Very often we don't even think about it. Well, everybody knows what is grain size, average grain size. Here we are clearly, for example, understanding that when we are talking about grain size, it have to be spoken about the grain size calculated by area. Why? Because if you will take, for example, this room, and we will try to put here, for example, elephants and monkeys, and then we'll calculate the average by frequency. Hardly in this room more than 3 elephants will be able to come, but monkeys can be thousands. So immediately elephants will lose without any chance to win in frequency. So this is frequency. But if we will calculate the volume which occupy elephants, then they can compete it to monkeys very well, because each elephant will really contribute. So this is the same things what we are having here. Then another question which was asked here, what is the size of the polycrystal? So again, this is some maybe not that much impressive, but I would like to show, yes, I know it is the end of it is the end of the story. So this is all our background work about how we can do calibration. This slide shows one trick due to my laziness. For example, the question, if I already have my phenomenological parameters, can I recalculate them into DigiMu? Straightforward. Yes, there is some chance, but with some limitations. If somebody is interested, I am ready to discuss it more. We tried dynamic recrystallization. Yes, we have got some nucleus. We have tried to do static recrystallization. We got the problem that all our nucleus got eaten. It means that here DG again reminds us that no, it is not take and press the button thing. We are dealing with the next level of complexity of software. It requests our inputs and our respect to it. So because of this, we are making our possibility of high performance computation, which you are welcome, and welcome to us to join this trip towards robust calibration and robust microstructural modeling. Thank you very much for your attention. We'll be happy to answer your questions.